So first, I would like to thank everybody for toughing it out to the very last session of this conference, everybody that's present. So I'm going to speak about classification with L2 regularization, and the model that I consider is something rather old-fashioned. I think the data lives in the unit ball of a Hilbert space. So things are kernelizable, and there is a distribution, like a probability measure, supported in this unit ball. And the measure is models the draw of the pattern vector and the label, the product of the label and the vectors. The label can be 1 or -1, so I don't have to worry about labels anymore throughout this talk. And I have a loss function with this technical property is not so important. It could be any non-zero number. And the algorithm I consider is also very old-fashioned. I minimize, I'm looking for the weight vector, which minimizes the sum of an empirical term of the average of the inputs, of the losses on the inputs, and in an L2 penalty or the square, it's like a square loss here, a square regularizer. And for the talk, I will assume, this is going to be one of the weaknesses of my result, is that I'm going to assume lambda to be fixed, this parameter, as well as, of course, the loss function is going to be fixed. The quantities that I study is the empirical risk, which is just the average loss that my weight vector gives me on the inputs, and the true risk, which is the expected loss on a new test point. And the interesting quantity is the difference between the two, which I would like to bound as the inputs are drawn IID from this distribution. So this has been studied a lot, and there is one very satisfactory, very nice solution by Bousquet and Eliseev 15 years ago. And they say that if the loss is Lipschitz, then there are two numbers which they only depend on the nature of the loss function and on the regularization constant. And then with high probability, the generalization error, or the difference between true and empirical risk, are bounded by the sum of two terms. The first term corresponds just to the expectation of it's a bound on the expectation of the generalization error. And the second term is the probabilistic bound that they get. And the way that they prove this result is that they show that with a stability analysis, they show that the generalization error changes only in the order of 1 over n if I modify one training point. And then they use the bounded difference inequality or McDermott's inequality, plug that in, and then they get this result. Because this is the expectation, the bound on the expectation. And so this is very nice, but it is very rigid also. It's like a worst-case result. It does not receive any benefit from potentially beneficial properties of the distribution. On the other hand, it makes no assumptions on the distribution, which is nice. So I was looking for a similar bound, which would make no additional assumptions, so it would hold in general, but at the same time, it would receive benefits if the distribution is in some way beneficial. So to get this, I had to, I wanted to use the same technique, stability technique, because, see, excuse me, let me just go back. The idea here is, and that's one of the very nice features, that you don't have to analyze the complexity of a function class, but you look directly at the algorithm and at the properties of the algorithm. So I had to find my own concentration inequality to do this, which is a generalization of Bernstein's inequality. And the generalization, so this first term, to cut it short, is just the maximal variation Like this is a finite difference operator, partial difference operator. It's the maximal variation in any of the training points. And the other term measures the interaction between different training points. So this is like think of it as this term as mixed partial derivatives. And think of the entire expression as the Frobenius norm of the off-diagonal Hessian of the function f. And with these two terms, you can control the deviation probability for functions of many variables. And there's the interaction term, and there is the same term as in Bousquet-Elisseev, or it's in McDermott's inequality. And the mixed partials, like if the function f is a sum of independent variables, then the mixed partials are zero. Because if I change one thing, it may change the function value, but it does not change the dependence of the function on another argument. So with this inequality, if the interaction term is zero, then it reduces to Bernstein's inequality. So this is really a generalization of Bernstein's inequality. And it turns out you can control the interaction term. I do it in a very clumsy way with differentiation. And you end up with this result, which is also the main result. And it says that for technical reasons, I require that the loss is 3 times differentiable. Then there's another constant, also only depending on the loss function and on the regularization parameter, such that with high probability I get this bound. This just comes from, it's the same as in Bousquet-Elisseev, this bound. Here I have a variance term, and then I have a term which goes down with 1 over n. So basically, if n is large, the number of observations is large, then the bound will be dominated by the variance term. And so if it just depends on it's a distribution dependent, but I don't make any assumptions on the distribution. I can compare it. I'm going to cut this short because I don't have much time. I can compare it to Bousquet-Elisseev and show that the variance term is always smaller than the corresponding term in the Bousquet-Elisseev bound. So if the 1 over n terms, if I disregard them, if I ignore them, then this result cannot be worse than that of Bousquet and Elisseev. But it can be a lot better. Because suppose you have a class of distributions which has the property that you can prove a bound on the generalization error with order n to the minus p. Just think of p as being 1, so it's like 1 over n here. That would be an extreme case. Then I can use this bound to show that my bound, I can use it to bound the variance of the generalization error, because I can bound the variance by the expected square, and I can bound the expected square first on a set of measure 1 minus delta. I can use this bound and plug it in, and on the set of measure delta, I just use the supremum, the maximum that I get for the generalization error, which is finite. So I get basically the same. I get the same bound with an additional factor of log n, and so it's basically the result is always squeezed in between optimal up to log n and worst case just as bad as the Bousquet-Elisseev result. So there's some things are improving the dependence on lambda, which is one of the weak points, or weakening the differentiability requirements, and more interestingly, apply the method of proof to other machine learning problems, because the concentration inequality, this is really also a benchmark for the concentration inequality that I found. So this is all that I wanted to say, and thanks for your attention.